So we learned how to draw Lewis structures last week for molecules, and now we're going to go a little further with that and draw Lewis structures for polyatomic ions. We're going to use the same procedure. Really the only difference is that we have to take the charge into consideration when we count the number of electrons. So for every negative charge we're going to add one electron, because if the ion has a negative charge, that means it has extra electrons, so we add electrons. If the ion has a positive charge, then we subtract electrons. And then when we're finished, we're going to show the Lewis structure in brackets and write the charge on the outside. So let's do cyanide ion. So the first step is to figure out how the different atoms are connected. There's only two atoms here, so that's not really, doesn't really require a lot of thinking. It must be carbon connected to nitrogen. And then we need to identify how many valence electrons are there. So carbon has how many? 4, because it's in group 4A. And nitrogen has 5, it's in group 5A. And then this negative charge means that we add 1 electron. So we end up with 10. So we're going to put a bond between the carbon and the nitrogen, and then we're going to distribute the rest of the electrons around. So that's 2 for the bond, 4, 6, 8, 10. And we're out of electrons. Do either of these atoms have an octet? No. We don't have octets on our atoms, and we've run out of electrons. That means we need to make multiple bonds. So we're going to take a lone pair from one of the atoms and make it into a bonding pair. So I'm going to erase that lone pair and make a bonding pair. We have the same number of electrons. Remember, the line is equal to 2 electrons. Now this carbon is 2, 4, 6, still not good. The nitrogen's better, 2, 4, 6, 8. We're still short electrons, so we're going to do that again. We're going to take a lone pair and make it into a bonding pair. And now each of these has an octet. 2, 4, 6 from the triple bond, and 8, 2, 4, 6, and 8. Everybody gets an octet except for hydrogen. Then this is an ion, so we're going to put brackets around it and put the charge on the outside of the bracket. That's just a convention. Master in Chemistry does not have the capability of doing the brackets. So you just leave the brackets off. And also, it forces you to put that charge on one of the atoms. So I'll just warn you, there's a problem where you do sulfate. And I'm not going to show you the whole structure because you need to figure it out yourself. But sulfate has a 2- charge. It doesn't want you to put the 2- on one atom. It wants you to split it up. So it wants you to put a -1 on one and a -1 on the other. And I really don't know how you're supposed to know that. That's why I'm telling you, warning you about that one. I think there's only one that does that, though. It's unfortunate is what it is. But this is the structure for the cyanide ion. Any questions? So same concept, we'll just have to deal with the charge. Let's do another one. This is hypochlorite ion. Chlorite was ClO3. Chlorite is the light version, ClO2, and this is one less than that, hypochlorite. So again, there's only 2 atoms here, so creating the skeletal structure is pretty easy. It must be the chlorine and the oxygen next to each other. Count up valence electrons. Chlorine has how many? 7, and oxygen has 6. And what do we do with the negative charge? We add 1, because a negative charge means we have an extra electron. So that adds up to 14. So I'm going to put a single bond between the atoms, and then I'm going to distribute the rest of them. So I've got 2 with the bond, 4, 6, 8, 10, 12, 14. This time I had enough. I didn't have to make any multiple bonds. Then I'm going to put brackets around this and put a charge on it because it has a charge. Any questions? If you forget to add the electron for the charge, you're going to run into trouble because you're going to end up with an odd number of electrons.
You add the electrons to the charge only for polyatomics?
You would add them for any ion. For any ion. We just don't often draw Lewis structures for monatomic ions. But yeah, it would be considered for any ion. Any other questions? There are exceptions to the octet rule. Sometimes you end up with a molecule with an odd number of electrons. And nitrogen monoxide is an example of this. Nitrogen has 5 valence electrons, oxygen has 6, 5 plus 6 is 11. There's no charge on it. And it is a molecule that exists in nature, it does exist, but we can't draw a Lewis structure that follows the octet rule because we have an odd number. So the best we can do is to put a double bond here. The oxygen has an octet, the nitrogen only has 7. So Lewis theory does not explain everything. Another exception is compounds involving boron. Boron is one of the smaller atoms and kind of, is an exception to some rules. Boron tends to form compounds where it has 6 valence electrons, or has, I guess you could call it a sextet instead of an octet. So boron trifluoride is an actual molecule, boron trihydride, an actual molecule, but there are not octets for the boron. So that was an example of something that had less than an octet. There are also some atoms that will take more than an octet, and these are called expanded octets. Sulfur can handle at times 12 electrons. Here phosphorus has 10. That's more than 8. That violates the octet rule, and yet this is what actually happens in nature. So the octet rule works for a lot of things. It doesn't work for everything. I'm not going to ask you to draw structures on an exam that involve violations of the octet rule. But I want you to know that these exist. Because if you go on and take Chem 1, I don't want you to say, "Oh, she lied to us. The octet rule doesn't work all the time." No, it doesn't. It works most of the time. It works really well in Chem 20. But even with these exceptions, Lewis theory is still a great theory. It's relatively easy to understand. It explains a lot of things, and it's very easy to do in comparison to some of the more complicated theories that we're not going to talk about.